Section 3, Newton's second law and various things that are related to it, like Newton's first law. Newton's third law is going to be a topic we save for another day. Only want to try and do so much in 1 week, you know. Force equals mass times acceleration. F equals ma. If you've ever taken any physics before, you've probably heard that. The force doesn't mean just, well, there's this force acting on the thing and that's what's equal to ma. It's the total of all the forces, okay? So, for example, if you're dragging a 50-pound bag of potatoes across the floor, the force that goes into F equals ma is not how hard you're pulling as you drag it. Rather, as you drag it along in one direction, there's a friction force pulling in the other direction. There's also a couple of vertical forces for that matter, but just thinking in terms of the x components for a moment, just what's going on horizontally, maybe you're pulling to the right with a force of, it depends on how rough the floor is. If it's a carpet, you're going to have to pull harder, but maybe you're pulling in the one direction with a force of 25 pounds and friction is pulling the other way with a force of 25 pounds. And so what goes into F equals ma is 0, okay? The total of all the force. If there are 17 forces acting on an object, it's the resultant of all 17 of them that goes in F equals ma, not just the particular force that's from you or that's caught your attention for some reason. Notation here, this symbol, like it says, that means a summation. Well, what it really is the Greek letter sigma, capital sigma to be precise. Sigma is a Greek S for summation. So add up all the forces and their resultant is directly proportional to the body's acceleration. We'll just think of this as being an experimental result, okay? F equals ma can be thought of as first principles. It's the assumption, one of the assumptions you derive other things from and not really derivable itself. We just believe it because people have been using it for stuff for 400 years and, well, more like 350. But it's always worked so far, which kind of gives you a lot of confidence. So experience has been for a long, long time that however much force you apply to something is proportional to that object's acceleration. Twice the force, twice the acceleration. 5 times the force, 5 times the acceleration. The constant of proportionality between these things is a property of the object called its mass, which one way of thinking of it is mass is how you define an object's inertia. Okay, inertia meaning an object's tendency to keep doing whatever it is it's already doing. It's resistance to acceleration. The example I kind of like is to picture yourself in a grocery store. There, I guess you've looked at that for long enough. Picture yourself in a grocery store with 2 shopping carts, one on each side of you, okay? One of them's empty, and the other one's piled as high as you could get it with frozen turkeys. So if you put a hand on each cart and push on them both with the same force, you're going to find that the empty cart picks up speed a lot faster than the one that's heaped up with turkeys. The more massive object has more inertia. the same force is quite a bit less effective at accelerating it. Likewise, if both of these shopping carts are coming at you, kind of like one on each side, and you stick out your hands to try and stop them both, you're going to find that the same force is much more effective in stopping the empty one. So the more massive object is harder to get moving in the first place. Once it's moving, it's harder to make it stop again. And this resistance to acceleration is called an object's inertia. And the way you measure an object's inertia is with its mass. Mass, as it says here, is measured in kilograms, or multiples or divisions of a kilogram. A gram, for example, would be a unit of mass. So F equals ma, Newton's second law. Now, Newton's first law, as it said there, easy enough to get it back. If Newton was publishing his work today, it would probably be Newton's 2 laws rather than Newton's 3 laws, because the first law is just a corollary to the second one. It's not a separate, distinct idea. It just kind of goes like this. Kind of nice to be here instead of home. It's a little bit more like an actual class, except for the fact nobody but me is here. But if I close my eyes, I can pretend. So the first law. The first law is the special case where the net force is 0. So if the summation of the forces is 0, if F is equal to ma, and if F is equal to 0, then A is equal to the 0, okay? Because assuming the thing exists at all, its mass is not 0. And so if this is 0, that's got to be 0. 0 acceleration is the same thing as saying a constant velocity. Writing that out in a little more detail. Acceleration is 0, that's saying that the derivative of the velocity is 0. Well, the derivative of a constant is 0, so you're talking about a constant velocity. Velocity is a vector. When I'm saying it's a constant, that means a constant speed and a constant direction. So Newton's first law put a big box around it because it's something important. If there is no net force on something, A body's velocity is constant, and that means it's constant in magnitude and direction. To phrase it another way, it's going to travel along a straight line at a constant speed. Any change in either one of those things requires a force. Okay, so that's how the first law follows from the second law. As I said, this is just a corollary to that. The general thing is Newton's second law. It's the reason Newton was making such a big deal out of it is, well, from our point of view today, it's for historical reasons. Newton was a young man when you were still in the final days of the arguments about whether the Earth actually goes around the sun or not. Maybe we should back up to the early 1600s when Galileo first came up with this idea. What we now call Newton's first law is actually due to Galileo, okay? Not to diminish Newton. I mean, Newton was a really smart guy, the kind of person who invents calculus on the side because he needs it for something he's working on that day. And Newton's laws contain a number of significant discoveries of his own, but maybe the most significant thing that Isaac Newton did, rather than, figure out the whole world entirely on his own, well, he said himself, I mean, this is a quote, "If I have seen farther than others, it is because I have stood on the shoulders of giants." He was referring to people like Galileo and Kepler and so forth, the people who'd gone before him over the previous 100 years or so. What Newton did is he took the isolated discoveries of these people. Galileo discovered the law of inertia. Kepler discovered the laws of planetary motion, and so on and so on. And he took all of these things that were just kind of sitting around by themselves, and he wove them all together into a complete, comprehensive description of the natural world. Okay, so anyhow, Newton's first law is originally due to Galileo, and as you may be aware if you know anything about the history of science, Galileo got in a little bit of trouble for going around saying that the Earth revolved around the sun. One of the arguments against the idea that the Earth is a planet was that, you see, Aristotle taught that for an object to be in motion, there had to be a force acting on it, which is, I mean, Aristotle was not stupid either. Let's see if that'll show it. I got to aim this a little lower. Okay. So Aristotle would have said, we've got this box here. Being in a state of rest is the natural state of this box. Notice that if I want it to move, I have to disturb that natural state by applying a force. And when I stop applying the force, it returns to its natural state. Well, that made enough sense that people believed it for close to 2,000 years. And really the only thing wrong with that is that people back then didn't think of friction as being a force in the same sense that pushing on something with your finger is, okay? But Galileo comes along and he says, now watch closely. The box doesn't stop moving the instant I take my finger off of it. See that? If the table had been even slipperier, and also quite a bit longer, it would have slid quite a bit further. If you could somehow make the table completely slippery, the box wouldn't have slowed down at all. Well, until it went off the edge of the table. So the first law is a complete philosophical turnaround from the idea that force is needed for something to move, right about there is a good place for that, to the idea that you have to have a force for something to stop. Here's the box going along the table. And of course, there's a couple of vertical forces also that they just cancel each other out. The thing we're interested in is here's me pushing on the box, P for push, and acting along the surface here between the box and the table, we have friction pushing the other way. These two forces are, if I'm keeping a constant speed, these two forces are the same size. So this is the case where there is no net force. And therefore, in this case, it keeps a constant speed, okay? It doesn't say there's no forces. It says whatever forces there are cancel each other out. So sum of the forces equals 0 until I take my finger off of it. Well, that force I call P comes from contact with my finger. When there is no contact with my finger anymore, the force is gone. Now you have an unbalanced force, which makes the box accelerate. A negative acceleration in this case, slows down. So, as I said, a complete philosophical turnaround from the idea that force is needed to maintain motion to the idea that a force such as friction is needed to make something stop. So the old argument was, because even in the year 1600, they knew the sun was really far away. So if the Earth was going to go all the way around it in 1 year, it had to be going thousands of miles per hour. This is at a time when 30 miles an hour was thought of as a terrifying rate of speed, okay? So if the Earth is going around the sun at thousands of miles an hour, any loose objects, loose meaning there isn't any force acting on them to propel them along, any loose objects, you, for example, would be left behind. And since you don't find yourself floating around in space, sadly watching the Earth disappear off into the distance, what was Copernicus thinking? The Earth moves? Obviously completely contrary to the well-established laws of physics. Or, well, back then they would have called it natural philosophy instead of physics. Well, along comes Galileo, and he says, well, you know, you keep moving just because you're already moving. I mean, some of you might be wondering about gravity also. Well, you stay on the Earth because gravity holds you down. And, well, that's a factor in the case of the Earth. But even if you were sitting on some silly little asteroid with a diameter of 10 feet, okay, like a little mini planet that you could fit in this room if you could get it through the door. The gravitational field of an object that size is so small you might as well ignore it, okay? If you just hiccup, you're going to throw yourself into space on an object like that. But you would, as long as you don't get the hiccups, you would sit on that asteroid day after day as it moves thousands of miles an hour around the sun, because an object in motion remains in motion. There's no force on you to make you stop, okay? Remember, Galileo lived, about 3/4 of a century before, well, I mean, he lived to be a pretty old man, but at the time he was getting himself into trouble for this sort of thing. It was like 65 or 70 years before Newton published his book. And the idea of universal gravitation was still many decades in the future at that point, but you don't need it. The law of inertia is enough. So anyhow, that's Newton's first law. Another thing you can do with Newton, now that we've got F equals ma under our belts, is explain how our system of units works. So maybe I should point you back at the handout here for another minute or two. To get further down the page, we put another book underneath it. I mean, yes, I could get all sophisticated and document share on the computer there, but I don't know, this just seems less cumbersome. Maybe I'm wrong. Well, you can read that pretty well. So, the way a system of weights and measures works, we're here right now. You need a small number of fundamental units, or sometimes they're called base units. For the time being, that's going to be the kilogram, the meter, and the second. Okay, the SI unit is actually based on 7 base units, but as long as we're just talking about mechanics, the branch of physics that we're in now, you just need those 3. I mean, another one of the fundamental units, for example, is the Kelvin, the unit for temperature. But if you're just talking about velocity and acceleration, you don't have to get into that. So in mechanics, 3 base units. The basic definition of these has been revised several times through the history of the subject. I didn't really get into that too much on the thing there, but just to give you a little background information. As an example, the original definition of the meter was based on the circumference of the Earth. The metric system originated during the French Revolution. It was one of the better ideas they had during the French Revolution, as opposed to, you know, cutting off everybody's head, which was kind of questionable. They said, well, and you know, this thing was all set up by a bunch of philosophers. People got more practical in the follow-up. But the original idea was, let's make the distance from the North Pole to the equator exactly 10,000 kilometers. That was the original definition. Well, that didn't last too terribly long, because every time you want to calibrate your instruments, you have to send out, I mean, nobody'd ever even been to the North Pole at that point. I think it was sometime in the 1800s that, I could be wrong, maybe I'm thinking of the South Pole. But anyhow, before very long, what somebody said is, you know, what would work a lot better is if we just got a metal bar made out of some nice alloy that doesn't corrode and doesn't expand or contract an awful lot, you know, something expensive sounding. Let's have some platinum in it. And we're just going to put 2 scratches on that bar. And we're going to have, as close as possible, we're going to put the distance between those scratches 1 meter apart based on the old definition. And now going forward, that'll be the new definition. It'll be by definition the distance between those 2 scratches. And well, yeah, that was an improvement. And that was the definition of the meter for many years. But there was a couple of problems. One is, it's nice to have, well, the solution to all the problems is it's nice to have a reproducible standard. Something that anybody, no matter where they are, can calibrate their instruments without having to go to Paris, okay? If you're in New Zealand, it's kind of a long trip to go to Paris and get them to let you look at the standard meter if you want to calibrate what you've got against the basic definition. So the other problem is, what if the bar had gotten blown up during World War II? Where would we all be then? So better to have some reproducible standard that anybody can use without having to refer to some artifact like that bar. Well, there was another definition used in between, but for about the last, I don't know, 15 or 20 years or something like that, the definition of the meter has been in terms of the speed of light. The speed of light can be measured to a ridiculous number of significant figures today. And time can also be measured extremely accurately with atomic clocks. So the distance that light travels in a certain very small fraction of a second, that is the current definition for a meter. There are similar definitions. There's a similar definition for the second. It's no longer in terms of the rotation of the Earth. It's in terms of, well, anyhow, enough said about that. The point is, there's some kind of an experiment you can do, and the result of that experiment can serve as a definition for these three base units: the meter, the kilogram, and the second. Now, what about a unit for speed? Well, you don't have to do some experiment where you'll like put a certain exact amount of powder in a gun and put a bullet with exactly the right mass in there, and when you fire it, the speed that the bullet comes out, that's going to be our unit for speed. Rather than something like that, where you're defining the unit with some kind of experiment, instead, our unit for speed, or velocity, is defined in terms of other units. Same thing with a unit for acceleration. Under my camera a little more here so you're not looking at this at a funny angle. Again, for acceleration, instead of the unit being defined with some sort of basic standard or experiment, it's I guess that goes about there. It's a unit that's defined as a combination of other units. Well then, I should probably give this a title. Talk about units. So what are we going to use for a unit of force in the SI system? SI, by the way, stands for International System, which may seem to you like it should be IS, but either the French say everything backwards or the English say everything backwards, depending on whether you're French or English. So in the SI system, let's say I had a box full of latex. Oh, those aren't latex, they're vinyl. A box full of vinyl gloves, a rather large box of vinyl gloves. It's a kilogram, exactly. And let's say you apply some force F. There's a string that's been attached to this box, and you pull on it, and you carefully adjust how hard you're pulling so that the acceleration of the box is exactly 1 meter per second per second. How much force would that be? Well, according to Newton's law, and in this case, the summation of the forces is just this one force F, because there are no other forces. Well, the numbers are not particularly hard to handle here. 1 times 1 is 1. The point of all of this is the units. As I've probably already mentioned, units can be manipulated according to the same rules that you would use to do arithmetic on numbers. So kilograms times meters per second squared is what we have here. And so that would be the SI unit for force. Kilograms times meters per second squared, meaning the amount of force that would give 1 kilogram an acceleration of 1 meter per second per second. There's only one thing wrong with it. It's just a terrible name. Nobody wants to go around saying that. Oh, my diet's working really well. I've already lost 15 kilogram meters per second squared. You're never going to get people to say that. So let's give this combination of units a name of its own. We use Newton's law to come up with it. Only seems fair to name it after Newton. Most of the units in the SI system are named after somebody. Watt, ampere. I mean, there was never a Bob kilogram, but with a few exceptions like that, they are named in honor of people who seem to be appropriate to name things after. Well, over here on the handout, oh, well, before I get to that, a Newton's a kilogram meter per second squared. Why should you care? Is this something that's just of interest to, people who are just really into weights and measures? The reason you should care is because you fear this. I use a lot of red ink on this. Let's say I hadn't labeled that as 1 kilogram. Let's say I had put 1,000 grams, which is of course exactly the same thing. And I said to the class, I want you to calculate this force. There would be a significant number of people who said, okay, the mass is 1,000 grams, the acceleration is 1, so 1,000 times 1, the answer is 1,000 newtons. No, it's not. A newton is a kilogram meter per second squared. If the mass is in grams, you're going to be off by a factor of 1,000. Now you might just say, it's only a decimal error, but if they ever made one of those decimal errors on my paycheck, I might give some serious thought to what countries do not have extradition treaties to the United States. Well, I wouldn't really, but it might cross my mind. So here, let me grab the formula sheet, which I think I have right here. Yes, how convenient. The last page of the formula sheet. Notice there is this column that says standard SI unit, length meter times second, and it goes on down, pascals for pressure and all that sort of thing. Pascal was somebody's name too. For any kind of calculation, whether it's F equals MA, whether it's pressure equals force per unit area, whatever formula you're using, if you put the standard units in, you will get the standard unit on your answer. Okay, so stick to the units in that column there, and you will not go astray. If you're given grams, convert to kilograms. If you're given centimeters, convert to meters, and so on. If you're given hours, convert to seconds. So, because the SI system is set up in a way that the units all fit together that way. Now, from time to time, we will brush off the old traditional British system of units in this course. These days, I always kind of hesitate and stumble when I call them British units, because Britain converted to the metric system almost 50 years ago. It's kind of interesting, actually. My wife watches a lot of craft videos on YouTube, and if the person who is telling you how to do something is old, okay, she'll say, well, now you need to cut this off so that it's 4 inches and blah, 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 blah. But if the person is young, they'll say, well, now you need to cut this off so that it's 10 centimeters, because, you know, with any kind of transition like that, you don't really complete it until all the old people have died. But anyhow, in the United States, it all depends on what company you're working for and what industry you're in. But measuring things in feet and pounds and so on is still a fairly common thing in the United States. Not in the rest of the world. America is kind of unique that way. But since a significant fraction of the people who take this course are engineering majors, and engineers could very well end up working someplace where they work in pounds and feet, I think it's still a good idea to introduce people to that system as well. Plus, the contrast is kind of nice. It's like, I actually learned more about grammar by taking a foreign language than I did in English class. And it gives you some sense about how a system of units works if you've got more than one example, so you can compare them to each other. So in what would have been British units half a century ago, some people are sort of getting in the habit of calling them US customary units now. In that system of units, force is measured in pounds. Once again, so that's unit of force. Maybe I should lower that just a bit. Just like in SI units, a unit of force has to equal a unit of mass times a unit of acceleration. If you're going to work in customary units, mass is measured in an obscure little unit you may never have heard of called a slug. I believe the origin of the name does not have anything to do with those icky little creatures you find on the bottom of a board that's been left out in the rain. Rather, the idea is mass measures how sluggishly something behaves. Inertia equals sluggishness. Well, wherever the name came from, that is the unit of mass. Now, as far as what are the basic standards used, you know, the definitions for these units, if you're in this system here, well, in a sense, the United States has been on the metric system since roughly the time of the American Civil War. If you send an email off to, oh, it's not the National Bureau of Standards anymore. I forget what they call the, you know, they always have to change the names of things every few years just to keep us on our toes. Whatever the name of the agency is now, if you ask them, what is an inch? They will tell you an inch is 2.54 centimeters, okay? So even if you're working in British units, it still goes back to the basic standards used in the metric system. But again, the reason for knowing this is that if you're dealing with a car that's going 50 miles per hour and you go to do some kind of calculation, miles and hours, no good. You got to have feet and seconds. And then something, yeah, it's right here in the note packet. Back over there again. closer so it's bigger and easier to read. Right here. And it is not a coincidence. I am highlighting this with my red pen because this is another thing that I have drained red pens on over the years. This is a very common mistake. Don't mix up units of force with units of mass. There's always people who are trying to measure force in kilograms. There's always people who are trying to measure mass in pounds. Naughty, naughty, naughty. Don't do that. You have no excuse because you can use this right in the middle of a test. That's what it says on the first line. Refer to it on quizzes and exams. And you will find that on the line that says mass, it says kilograms. And over here, it says how many kilograms equals a slug. The part about pounds is very carefully phrased. I didn't say a kilogram equals 2.2 pounds. I said a kilogram weighs 2.2 pounds if G has a certain value. If you're on Mars, a kilogram weighs something else. Okay. You find newtons and pounds down here on the line that says force. So beware the red pen. Got him. I don't know what a fruit fly is doing in here, but it is no more. Okay, so don't mix up those. And the relationship between weight and mass is the next thing on the list here. Clock is running. As usual, I got too long-winded about the weights and measures and things, but I suppose a nice thing about doing it as a recording like this is if I get 5 or 10 minutes too long-winded, everybody doesn't just walk out at the end of the period. I can just let it record for another 5 minutes and you probably won't notice. So I already pointed it out to you. So the word weight means the force of gravity. How hard does the gravitational field you're in pull on you? Mass is how much stuff is there, how many turkeys are in the shopping cart. Or if you're a vegetarian, how much celery have you piled up in there? So let's consider a freely falling object. If I was to take the eraser and drop it, I'm not going to because it'll make a mess on the floor and that's not nice to do to the cleaning people, but here it is on the way down. We have an object of mass m, and I have illustrated all the forces acting on it with arrows. Well, there's only one force. That's what the phrase freely falling means. Let's apply Newton's law to this situation. Add up all the forces. Well, there's only one force. It's like add up the following numbers, 7. The total is 7. And if you add up all the forces on this, it's the weight. Recopy the m. The acceleration of a freely falling object, we've been using the letter G to stand for that. There is the relationship between weight and mass. Maybe I should clarify one thing. Sometimes people use A and G interchangeably. Well, write down some equation and it's got an A in it. Oh, I should stick in 9.8 for that. A and G are only the same thing if an object is freely falling. That, didn't really need to draw a picture of it, I suppose, because it's right there. That is the eraser sitting there on the chalk tray. Okay, and it's just sitting there minute after minute, not doing anything at all. So its acceleration is 0 because the forces on it cancel out. Okay. In addition to gravity pulling down, there's the chalk tray pushing back up on the eraser, and the total force is 0. No force, no acceleration. It's obeying Newton's first law. This other symbol, G, letter A stands for what the acceleration actually is. The letter G stands for what the acceleration would be if I dropped it. They are only the same thing if somebody has dropped it. But back to this, I considered a special case in order to develop this, but once I've got it, it weighs the same thing, even if it's just sitting there. Even if it's not freely falling, it's still the same amount of mass, the same distance from the center of the Earth. So W is no longer the net force. There are other forces aside from the weight, but as far as that individual force, it weighs the same thing sitting there as it would if it were falling past the tray. And so in general, weight equals mass times gravity. If you have 1 kilogram, it weighs 9.8 newtons. Okay, so now, back to the handout. Done the relationship between weight and mass. And as I said, primarily we're going to use the SI system in this course, but not exclusively. And so here's a case where we're going to use feet and pounds instead of meters and newtons and kilograms and so on. 3,200 pounds for the car. 88 feet per second is 60 miles an hour, okay? So this car, this is not exactly really high performance, but this particular vehicle goes from 0 to 60 in 10 seconds. But remember what I said about you got to put the standard units in to get the standard units out. 60 miles per hour, can't do that. It's got to be feet per second. So 60 miles an hour equals 88 feet per second. And tells us some other stuff. The question is, how large is the friction force? So, I'll be just a moment. Eraser, making a spot to write. This is going to be a two-step kind of thing, okay? Step one, calculate the acceleration from the information that was given. And then step two, once you know the acceleration, put it into F equals ma and solve for the force that the question asks for. So First of all, yeah, maybe I'll write this down first and then do the first example. Example about the car in just a moment. But first of all, a general point. Sum of the forces equals m times a is a vector equation. Okay, this is a vector sum. You have to either use the head to tail method or add up the components or any of that stuff we did in section 2. Mass is a scalar, but m times a would be a vector. This vector equals that vector. It is often convenient to take a vector equation like that and separate it into a couple of scalar equations. If two vectors are equal, that means they have the same components, okay? So the x component of the net force has to equal the x component of MA, and the y component of the net force has to have equal the y component of MA. And you know, these equations would just be full of numbers, which is kind of convenient instead of trying to deal with a bunch of arrows. Okay. So that is background not only for problem number 1, but for pretty much everything else that has to do with F equals MA. Step 1, find, well, it'll be the average acceleration actually. Question doesn't say necessarily that the acceleration was constant. Average acceleration will give us the average force, which is the way the question is phrased. Find the average force. Change in velocity over change in time. Well, it goes from 0 to 88. That's a change of 88. Time needed for the change, 10 seconds. So the acceleration of this car is 8.8 feet per second squared. Now the F equals MA part of it. When you're doing an F equals MA problem, it's a good idea to start out with a diagram showing all the forces. The more complicated the situation, the more important the diagram becomes. This is a relatively simple problem. So just the same, for somebody who's just starting out, always draw the picture. I mean, really, how much time is it going to take you? There's always a picture. If you get really good at it, sometimes in a simple situation, you might be able to have the picture in your head, but anyhow. Unless you're floating around out in distant reaches of outer space somewhere, there's always going to be gravity. So the car's weight pulls down. There's the supporting force from the road pushing back up. These two cancel each other because the car does not, you know, fly away or something. It's a car, not a helicopter. So vertically, you're maintaining a balance with the forces. The question says that the force propelling the car forward, the force that's ultimately due to the engine, is 1,000 pounds. Pointing the other way would be the force of friction. Friction always opposes motion. If the car is going that way, friction points the other way. This is actually the total of a couple of different effects. there are two distinct types of friction acting on a car. There's rolling resistance in the tires, and then there's also air drag as the car pushes through the atmosphere. And we're just going to use a single arrow to stand for the total of all of that. So, summation of the forces in the x direction. Well, in general, the sum of the forces in the x direction is equal to ax, but this car is accelerating right down the x-axis. There is no y component, okay? So ax is equal to just plain a with no subscript because ay is equal to 0. So sum of the forces equals ma because it's accelerating in the x direction. Every place you have a horizontal arrow on the picture, that becomes one of the terms in this summation. So pointing to the right, we have 1,000 pounds. Pointing to the left, we have the friction force. Since it's to the left, that gets a minus sign. Positive to the right, negative to the left. Now, here's where the red pen would come out. Very common mistake. Mass of the car, people put in 3,200 pounds. A pound is a unit of force. The question doesn't spell it out. It doesn't say this is the car's weight or this is the car's mass, but you can tell by the unit, okay? If something is measured in hours, you know that's time, not volume. If it was volume, it would be measured in gallons or cubic centimeters or something like that. If it's hours, it's time. And in the same way, if it's pounds, it's force. In particular, the 3,200 pounds is this force here, the gravitational force pulling on the car. So you have to calculate the mass from, it's over there at the right where you can't see it right now, but remember there was W equals mg. So if W equals mg, that implies that m, which is what you need to have in there, m equals W over g. So 3,200 pounds divided by, well, in terms of how many points you would lose if this was on a test of some sort, the worst mistake would be to just stick in the 3,200 pounds for the mass. What would cost you significantly less points, but still cost you some points, is there would be people who stick in 9.8 for G. You have to use a consistent system of units. G is 9.8 meters per second squared. We're not working in that system of units. You need G in feet per second squared. Did I put 32.2 or just 32? 32.2, okay. So M equals that divided by that, which is 99.4 slugs. More space to write. Acceleration I'd figured out earlier. Notice how the units work out. Feet per second squared here cancels feet per second squared there, leaving you with pounds. So when I solve for F, it's going to be 1,000 pounds minus another number that's in pounds. In order to add or subtract, things have to be in the same units, okay? If I asked you, how much is 5 gallons plus 3 hours? The answer is not 8. There is no answer because it's a dumb question. You can't add 5 hours to, no, what did I say? Whatever I said, you can't add them because they're two different things, okay? Well, if you already have 5 gallons and then you add another 3 hours, that's just gibberish, okay? To add or subtract, things have to be in the same units. So this is going to be, when I solve for F, it's going to be pounds minus this, whatever this works out, 2 pounds. Keeping an eye on the units is a good way to keep yourself out of trouble, okay? Introductory students kind of underappreciate the value of dimensional analysis. Are the units working out the way they should on things? It's a good way of avoiding mistakes, or if you've made a mistake, it's a good way of locating where you made it. You go through the calculation, and when you get to the line where the units don't make sense anymore, that's where you made the mistake. Anyhow, go shift the camera over. We've got 1,000 minus F is 39 point. It's not really necessary to write it out in this much detail, but in the end, what you've got is 875 pounds there. But I thought I'd, emphasize once again that mass is measured in slugs. So sometimes you get out an old book that's written in this system of units. Sometimes they just avoid this unit by rewriting the equations. Instead of F equals MA, it's F equals W over G times A. Any equation where the mass occurs, they just put W over G. Because let's face it, slugs are a little on the obscure side. So a little bit of algebra, subtract the 875 from both sides, add the friction force F to both sides. And I think I'll go through one more example in this recording. Like I've said earlier, even though the class is scheduled to meet 3 times a week, seems like I might as well just break it into 2 recordings per week. And, if you don't want to sit through an hour and a half of this kind of stuff, you can watch it 5 minutes at a time. If you have a really short attention span, that's the beauty of a pre-recorded video. So let's slide you back over here. I'll go to the bottom of this page, and then looks like I need another book under there. Go to the bottom of this page and then start the next video at the top of the next one. Okay, you have a box which weighs 100 newtons. And for some reason that we don't get into, you decided to hang that box from a couple of ropes. This is supposed to be the wall, and this is supposed to be the ceiling in whatever room it is that you're doing this in. And the question is, find the tension in each of those 2 ropes. And it kind of explains the word tension there. The tension is the force in the rope. Each little piece of the rope pulls on its neighbors. At the very end of the rope, the ends pull with this much force on whatever they're attached to. I shouldn't have moved that so soon. The one end of the rope pulls on the wall with that amount of force. The other end of the rope pulls on the knot here where all the ropes are tied together with that much force, and everywhere along it, each little piece of rope pulls on its neighbors with that much. It's the amount of force in the rope that's trying to pull it apart. And if the tension becomes too great, it will succeed and the rope will get pulled apart and your structure fails and the box falls down on the floor, which is not probably something with a lot of consequences, but the principle here is the same as what's used in the design of any kind of structure. If you are building a bridge, you don't just do it by trial and error. It's like, oh, well, spent $100 million and that one fell down. Well, next time we'll make it stronger and see how that works. No, they aren't going to give you a next time. You have to go through and figure out how much stress each member in the structure is going to be subjected to so that you know how strong to make it. Now, not too many people actually hang boxes from a system of ropes like the one that I drew here, but you know, this is an introductory course. You don't have people walk in one day, like the third week of the semester, and say, okay, class, today you're going to design the Brooklyn Bridge. That would probably not fit in a 55-minute period. So let's consider a simpler structure that would involve some of the same principles to kind of get your feet wet that way, okay? You figure out how much tension is in each one of those ropes. That tells you how strong of a rope you need if you're designing this thing. Now, if you're just hanging a box in your garage, you can get away with just picking some rope that's that big around and saying, that'll hold it. But in a more serious application, well, obviously you don't want to pick something that's too weak, but maybe what's less obvious is it's also bad to design it too strong. The problem with too strong is that strength generally equals cost. If you're designing an airplane, every pound of metal that you put in that airplane equals many gallons of fuel over the lifetime. That thing's going to be flying around for probably the next 30 years, maybe longer. And like I said, every pound of fuel or every pound of metal equals many pounds of fuel. So you want it to be just strong enough that you never have any problems. Any stronger than that increases the cost unnecessarily. So you need to go through and figure out this piece needs to be that strong, that piece needs to be that strong. And that's what we're going to do with these ropes with the box hanging off of them. So the first step is always the diagram. Do not skip, it's called a free body diagram. Do not skip the picture. The equations come from the picture. If you can't draw the picture, you're not going to be able to get the equations. So I guess really the first step is just simply to answer the question. Summation of the forces on MA equals M times A. Summation of the forces on what? Acceleration of what? Well, in this case, let's go with the knot. The knot where the three ropes all come together. That's a good choice because some forces we know come together with some forces we don't know. And so there's the knot. And there are three forces acting on it. Pulling downward would be 100 newtons. going right straight to the left. The tension, you can name these anything you want. I mean, it's just a name. I used T for tension, and then a subscript for, rope number 1. And for the tension in rope 2, I called it T2. If you don't like subscripts, you could call them A and B. I've always been sort of tempted. I've never actually done this. I really should someday. I've always been tempted to use names like Bob and Alice. It doesn't matter. Just since we don't know how many newtons these are, you need some sort of name to stand in for the number until you can figure out what the number is. With flexible rope, well, not only with a rope, but with a chain or any kind of flexible cord, the force is always right along the cord, okay? Go home, get a piece of dental floss, try to push something with it. Cords, strings, ropes, chains, they always act in tension, never in compression. They just kind of fold up if you push on them. Furthermore, you can't push anything to the side with them either, okay? Strictly in tension. So if this rope is horizontal, the force it exerts on that knot is horizontal. And if this rope is 30 degrees above the horizontal, then the force it creates is 30 degrees above the horizontal. This is in contrast to something like a rod, okay? If you had like a solid steel rod welded to another rod here and a third rod goes down to support the box, you don't know the magnitudes or directions of the forces in that case, because with a solid rod, or like an I-beam or any sort of solid, you can push to the side, you can push or pull, the force could be in any direction. But with ropes, it would just be like this. Okay. Once you have identified all the forces, the diagram here is a bookkeeping technique, okay? Makes you take inventory of all the forces acting on that particular object. Once you've done that, the next step is components. Well, this one lies right on the x-axis, so its components are trivial. And this one lies right on the y-axis, so finding its components is also trivial. You just got 0 for the x component and negative 100 for the y component. This one that's at an angle, well, that takes a little more work. Let's make a little sketch of it over here. Came out a little bigger this time. Well, I never did claim this was drawn to scale. Same sort of thing that we've done before. Hypotenuse times sine is the opposite side. Hypotenuse times cosine is the adjacent side. Mistake I see once in a while in a problem like this one, people will say 100 times the sine of 30. They just have to have a number. They just can't stand the uncertainty. They just have to have a number. They can't use a letter. They put 100 times the sine of 30, 100 times the cosine of 30. The 100 points right straight down at 270 degrees, okay? This force is unknown. It's one of the answers. If you knew T1 and T2, you'd be done. You could go on to the next thing, okay? So the symbol has to stand in for the number until you know the number. It's this unknown force times the cosine, not 100 times the cosine. 100 is this force, not that one. Well, for an object at rest to remain at rest, the net force on it must be zero. I've had people ask me, well, how do I know when to use F equal, sum of the forces equals MA versus using sum of the forces equals zero? And the answer I give is the summation of the forces always equals MA. But if you have an object at rest remaining at rest, okay, if you're talking about a piece of steel in a bridge that's been just standing there in the same place since 1927, its acceleration is zero. So the reason that that's the Y components. The reason that the sum of the forces in the Y direction is equal to zero is because AY is equal to zero. In general, sum of the forces in the Y is equal to M times AY. In general, sum of the forces in the X is equal to M times AX. But in this particular problem, the acceleration is zero. Not only is it not accelerating, it's not even moving, okay? So this special case of Newton's second law is very useful in the design of structures. If it's a dynamics problem where things are moving around, you solve it in pretty much the same way. The only difference is that instead of the sum of the forces equaling zero, the sum of the forces will equal some other number, M times whatever the acceleration is. You set it up the same way. It's, anyhow, here we have an object at rest remaining at rest. It's in equilibrium. Every place, I should probably have drawn the components a little bit more clearly. I started out with the Y components because let me just go ahead and write down both equations and you'll see why I'm starting out with the Y components. Every place there's a vertical arrow in the picture, that's one of the terms in this summation. And there are two vertical arrows. There's the 100 pulling down, there's the T sine 30 pulling up. So up is positive, down is negative. Every place there's a horizontal arrow on the picture, including components. Any place there's a horizontal arrow, that goes into the X summation. I've got T1 to the left, I've got T2 to the right. So that's what I meant by the equations come from the pictures. Every horizontal arrow becomes a term in the summation. And the reason that I wrote down the Y components first instead of doing it in alphabetical order is I recognized that I was going to get an equation that has just one variable in it out of the Y components, and I can solve that, so that would be the place to start. The worst case scenario is you end up with a system of two equations with two unknowns, and you have to, there's the addition method and the substitution method, and hopefully you remember your basic algebra. But things aren't quite that elaborate here. We can just add the 100 to both sides. And then you divide through by the sign. Let's see, this is T2. Forgot the subscript. There's one of our two answers. Maybe it's worth pointing out that that is significantly more than the weight of the box that all of this is supporting. So if you just kind of guessed and said, well, the box is 100 newtons, I'll get some ropes that can stand 150, that ought to give me a good margin of error. Yeah, it's going to break, because the ropes not only pull against the weight of the box, they also pull against each other. And so you've got 200 newtons in this one that goes at a slant. Now that I've got a number for T2, I can stick it in there. And now this equation only has one unknown. And now I'll be able to solve it. Add the T1 to both sides. That one's 173. And as I said, this is a good spot right here to make the break between the first and second half of section 3. So I won't say see you in the next recording, but you'll see me anyhow.